Okay, so now I want to get into the next topic right here. Something that we haven't covered so far is collisions. You know, you've probably been pounding your head against the wall this whole course, so you're probably pretty good at collisions now. But now we can go through the physics of it right here. And the opposite of a collision is an explosion right here. So when I say a collision or an explosion, you know, when we were just throwing a projectile, when it was in your hand and you were pushing it out, that's an explosion right there. Or when you catch the object or when it hits the ground, that's a collision right here. We were always looking at our projectile motions after it left your hand and before it hit the ground. But now we can look at it while it's exploding in your hand or hitting the ground or other collisions right here. So how do we handle collisions right here? You know, let's just say we have a ball and we just drop it and it hits the ground, and we ask, what is the force on the ball when it hits the ground right there? That is, if I just have this object right here and I just dropped it on the ground, what would the force be when this thing hits the ground right here? Well, it's not easy to answer, because suppose I have two objects, this object and another identical one, but one is wrapped in a spongy material and this one isn't. You'd probably rather have the spongy one dropped on your head. Why? Because it's more squishable. So the force here really depends on the squishability of the object. And I don't want to have to worry about the squishability of every object. So we'd like to be able to work these problems out without dealing with forces right here, or the squishability of it right here. So what do? How do we handle these if we're not going to look at forces right here? Well, if we go back to Newton's second law right here, which was F equals ma. It's really the sum of the forces equals ma right here. Well, I should tell you, Newton never said this right here. This isn't quite the truth right here. It's just that you couldn't handle the truth. Now I think you can handle the truth a little bit better. What Newton did say was, he said the sum of the forces is the derivative with respect to time of mv. That's what he said right there. And you'll notice, if you are taking the derivative of this, if m is a constant, I can bring it out in front to make it m dv dt, and dv dt is acceleration. So this is really only good when the mass is constant. Well, all of our problems, the mass has been constant. So this has been fine for everything we've done. But if the mass ever varied, then you'd have to take the product rule on this derivative right here. So what Newton said is, why don't I give this mv a name? And I'll call it P, momentum. So he said, let's call P equal to mv, and we'll give it the name, we'll call it momentum. That way, the Newton's second law then just becomes the sum of the forces equals the change in momentum with respect to time. So that's really what Newton's second law was right here. Now, later on in the course, am I going to say, you know, that's not really the truth, it's really something else? And no, I won't say that. Maybe in another class I will, but not in this class. Okay, so now this is Newton's second law. So now let's say we have a collision. Let's say out in space. We have ball A is moving in this way, and ball B is moving this way, and they collide. And so what are the forces on them? There's no gravity. We're a long ways away from anything. Well, you notice that we have a normal force on A right there. There's a normal force on A. How about due to B? Right here, I'll call it normal of A due to B. And we notice we have an equal and opposite normal on B due to A. This is the normal on B due to A. And they're opposites in direction, so the one is equal to the negative of the other one. Remember, they're equal in magnitude, Newton's third law. So we do know that the normal on A due to B is equal to minus the normal on B due to A. They're equal and opposite. So let's apply Newton's law to let's say object A. The sum of the forces on A is equal to, there's only one force, NAB, and that equals the change in momentum of object A with respect to time. There's Newton's law for object A. For object B, we'll just write the same thing. The sum of the forces on object B, it's NBA, and that equals the change in momentum of B with respect to time, right here. Well, we just said that these two are equal and opposite. This is equal to negative of that. That means that this is equal to the negative of that. That means the derivative of PA with respect to time is equal to minus the derivative of B with respect to time. Or, let's bring it onto the same side. And so we got dPA dt plus dPB dt, and that equals 0. Or let's factor out the derivative with respect to time, PA plus PB equals 0. Well, the only time the derivative of what is always 0? Well, the derivative of a constant. That says that PA plus PB is a constant. Which means that you cannot, this is the total momentum of the two. If it's always a constant, then you could never destroy momentum. You can never create momentum. It's like energy. We could never destroy energy. So now we have something else that we can never destroy or create. And that means if it always stays the same, we can look at all the momentums before a collision, and we can look at all of them afterwards, and they should be the same. And that way we don't deal with the squishability. Remember, so this is all the momentums, M, move this over here. We can say all the all the M, this, how about if we just write it like this, the sum of, how about if we just write here, the total momentum before equals the total momentum after. Total momentum after a collision. Okay, so this is what we'll use, and so this is just all the MVs. Remember, these are just all the sum of all the MVs, M sub I, V sub i's. Before, it should equal all the sum of all the M sub I, V sub i's afterwards. Well, you notice this is a vector equation. It's not like our energy equation. That was a scalar equation. This is a vector equation, which means it's true for each component of space. You break up, remember, these are vectors, so you got to break them up into their components. So that means the total momentum in the x direction before equals the total momentum in the x direction after the collision. Same with the y and the same with the z right there. Make sure you don't need these vectors up here. Okay, so let's just suppose we have a block right here and it runs into another block right here. I'm just going to, on a frictionless ground right here. This thing has a certain mass and it has a certain velocity, so it has a certain amount of momentum. This one will just keep at rest. So that means this momentum, so this momentum would be mv, this momentum would be 0 because he's at rest. The total momentum of the two would be mv, right here, in that direction. If they collide with each other, the total momentum after the collision will be exactly the same. It will be mv. So if they, let's say it doesn't matter if they stick or don't stick or bounce off, it doesn't matter. But let's say they stick. If they stick, then together this thing will have a momentum which is the same as it was before, mv. Well, since the mass, what's happening when this thing collides, the mass gets bigger. If the momentum stays the same, and if the mass gets bigger, the velocity's got to get smaller. And we can see it right here on this, right here. Here I have, let's just say, I have a mass right there, and now I run into this thing right here. You notice when this thing hits this, the mass is growing a huge amount, so the velocity drops by quite a bit right here because I'm increasing the mass so much. So it really cut down the speed right there. So what happens if this one has the mass right here and I collide it right here? Well, this guy, he doesn't pick up much mass because this is already quite heavy. So if he doesn't pick up much mass, he's not going to lose much speed right here. The mv here, you've just made a little bit more m, but you lose a little bit of speed. Right? And that's why people like to drive big cars. So when they run into things, they don't slow down much right here. And you noticed if you hit a bug on your windshield, this is a small object right here. If you hit a bug on the windshield, you'll notice the bug is going a lot faster after the collision. Why? Because he wasn't going as fast as your car was. And so the bug lost a little bit of momentum, and he gained momentum because now the bug's going faster. You lose a little bit of momentum. Unless you're getting hit by bugs on the back window, that means you're driving too slow and they're pushing you right here. So what happens if they're exactly the same mass? If they're exactly the same mass, then when this runs into that, you've doubled the mass, so the speed gets cut in half. So the speed should get, it's kind of hard to tell, but the speed, when this thing comes in and hits, the speed is half the speed afterwards right here. So there's the case when you're running into each other. Well, let's look at the case where you just bounce off of each other. So we have this thing coming in, and let's say this is not moving. It's not moving, so this v equals 0. And let's say this thing runs into that one right here. So let's just, let me make one of them bigger than the other. I'm going to make this one bigger right here. So this is a big mass, and this is a little mass. And this one's not moving, and this one's moving right here. Well, if they don't stick together right here, I'm going to make up some numbers here. Let's just say the momentum of this is 10 units of momentum. This one, the momentum is 0 units of momentum because it has no speed. So the total momentum of the two after the collision, the two before the collision is 10 units that way. Now they bump into each other. And they're not going to stick. They're just going to bounce off. I don't know what the momentum of each one individually is, but I do know what the total momentum is. The total of the two has got to equal the same as the total before. It's got to be 10. So if I knew the momentum of one, I could get the momentum of the other. Right here. Well, this is a lot bigger than this. What's going to happen to this one after he runs into this? Well, this is a lot heavier. It's just going to keep going forward. But he's going to slow down a little bit. So let's just say afterwards, this one is going forward at, say, 8 units of momentum. 8 is the momentum of that one. Then what's the momentum of this one over here? Well, it's got to add up to 10, so this one is going at 2 units of momentum right here. This is what the equations will give us right here. Now, it doesn't mean that this one's going faster. It's just that most of his momentum is in his mass and most of his is in his speed right there. So this one has to go faster. You can't get in front of him right here. What happens if if this one were smaller, this mass were smaller than that one. If this one were much smaller right here and still going at 10 units, what happens when you run into something bigger than you right here? If you run into something bigger than you, then you bounce back right here. So let's just say after the collision, this one comes back at, say, I don't know, I'm just making these numbers up. How about 4 units of momentum? P equals 4. How much does this one have right here? And I'll tell you, it's not 6 right here, because we had 10 units this way. We have to have 10 units that way afterwards. If you put 6 there, you'd have 6 and 4. That would only give you 2 units this way. This one over here is going to have to be 14 units, because 14 and then minus the 4 gives you the 10 units right here. So anytime you bounce off something, that other object is going to get most of the momentum. Why? Because this object had to stop this one. This big one had to stop him, and then he had to kick him back. So that's why, if a ball bounces off of you, it hurts a lot more than if it sticks to you right here. So you might want to put Velcro all around you or something to make things stick to you. They won't hurt as much as if they bounce off. So now let's come back to over here, and let's look at this same case right here. Now if I want them to bounce off, I can just turn this around. And again, if this one is the heavy one, when he runs into this, he's going to continue moving forward right here. And so, whoops, I need to bring that down just a little bit. So afterwards, this guy slowed down a little bit, and he picks up a lot of speed right there. And then let me put this one over here. Now this one should bounce back right here. So this one bounces back. And what happens if they're both the same mass? If they're both exactly the same mass right here, then it does exactly what's in the middle. It doesn't go back or forward. It just stops right here. So if you run into something exactly as big as you are in your like a super ball right here, then you're just going to stop and the next one's going to take off right here. Okay, so this is going to be the whole rule for collisions or explosions right here. If we look at a bomb right there, you light this thing, what's the momentum before? It's 0. It's just sitting there. Then afterwards, you got all these pieces flying out right here. If you add up all these pieces, they better be the same as the momentum before, which is 0. So all the pieces that give you momentum so much this way, it's going to give you the same amount this way right here. Okay, and that way we don't care about the squishability. We just look at MVs before and MVs afterwards. So next time we'll start looking at some problems on this stuff right here.